efficiency. Cutting, threshing, digging, picking, stripping, shaking, and raking. Whatever the crop, there's usually a custom machine to harvest it. But where does the line between machine and human hands ultimately fall? Now, harvesting on Modern Marvels. "250 miles above the Earth, a satellite camera lens is focused and snapping high-resolution images. The subject is not a weapons factory or a military convoy. It's a field of cotton in central California. Digital Globe, an imagery and information company, operates the world's highest resolution commercial photography satellite. Its images have many uses, even for a growing number of farmers who are now using the high-res photos to gather intelligence on their fields to maximize the harvest.
When you stand on the edge of a field and you look across the field, it all looks the same. From the satellite, you can see exactly where things are. We're seeing areas that are weak spots and strong spots in fields. And this is where you make your management decisions that improve your yield, improve your production, improve your management of that crop.
In this particular cotton field, satellite imagery is helping to prepare the crop for harvest. Before the cotton bolls can be machine picked, the plants must shed their leaves. To accelerate the process, a saltwater-type defoliant solution is applied to each and every cotton plant. Before satellite photography was possible, a uniform amount of defoliant was applied to the entire field. Now the space-based photos give the farmer the power to cut costs with a process called variable rate technology.
Using our imagery, we can see the amount of vegetation that's present. We can create a map that shows that this is the denser area of the field, therefore it should get a greater volume as our defoliant. And this is a weaker area of the field, or a less dense, and so it should get less defoliant.
The helicopter spraying mechanism interfaces with a computer controller and a global positioning system.
So as the helicopter is flying along, the GPS system is telling it exactly where it is in the field. It's reading the map that's in its controller, and it's applying the appropriate rate of product.
The satellite is simply one more tool in the belt of the 21st century farmer. In a world where globalization has sparked fierce trade competition, improving the efficiency of the harvest has become a matter of survival. Finding new ways to substitute the human hand with better and faster machines has revolutionized harvesting in the last 2 centuries. But before machines came to dominate the fields, harvesting crops was decidedly less complicated. Between 6 and 7,000 BC, in the Middle East, the first hand tool used in the act of reaping or cutting was a straight knife made of bone. In the same period, the Egyptians began using flint-bladed curved sickles. The forward curve of the blade enabled a worker to cut more quickly through a handful of standing grain. As sickle designs improved, a worker was eventually able to cut nearly 1 acre of wheat per day. But millennia of stooped, uncomfortable work with a sickle finally yielded a simple upgrade. In 9th century Germany and other northern European nations, one of agriculture's most important advances revolutionized the grain harvest. The long-handled scythe had a much larger sickle blade designed to be used in a standing position. With a scythe, a man of average strength could cut 3 acres of wheat in a single day. But the scythe had a major drawback. When the blade cut the wheat stalks, much of the grain was lost when it fell and shattered on the ground. The final improvement of the scythe was born in North America during the colonial period.
So what they did was they put a little wood basket behind the sigh, and that was a cradle, and that was an enormous and sometimes forgotten evolution in grain harvesting.
The cradle caught the cut wheat before the grain could shatter on the ground. In the vast grain fields of America, the size of a farmer's crop was limited by how quickly the grain could be harvested. In the 19th century, gangs of traveling laborers were necessary to harvest the growing acres of wheat America needed for its tables. Farmers needed a better method. It is often hotly debated who invented the first successful mechanized reaper. In 1831, a Virginian named Cyrus Hall McCormick debuted his version. In 1833, a Maine Quaker named Obed Hussey made it a competition. Both machines were revolutionary, but a head-to-head contest in 1843 determined that McCormick's reaper was superior. Hussey's machine couldn't seem to cut wet grain. The McCormick reaper signaled the dawn of mechanized harvesting. Its design was simple. When pulled by a draft animal, a single ground wheel powered a horizontal blade that cut the stalks as the reaper moved forward. The ground wheel also powered a rotating reel that pulled the cut wheat onto a platform. One worker raked the wheat off the platform into piles for later bundling. A second worker rode the horse. It was a simple concept that enabled two men to cut up to 12 acres of wheat in a single day. A critical milestone in agriculture. The U.S. government decided that McCormick's reaper was far too important to let one man control production. In 1848, McCormick's bid for a patent extension was denied. The reaper simply cut the crop. The grain kernels still had to be threshed. That is, separated from the chaff or plant stalk. For this, mechanized threshers replaced the age-old task of hand flailing the grain kernels to separate wheat and chaff. While most believed that the future would revolve around the reaper and the separate threshing machine, one forward-thinking Michigan tinkerer disagreed. In 1835, Hiram Moore was inspired by a friend's dream. In the dream, a huge machine drawn by horses was cutting and threshing great quantities of wheat in a single operation. Moore pursued the dream and constructed the world's first combined harvester.
Early reapers simply cut the wheat, but it still had to be threshed at a later date. The combines combined the thresher and the cutting apparatus into one machine.
Moore's combine cut the wheat, then used a rotating cylinder with spiked teeth to thresh the grain kernels from the stalks. Eastern farmers were already sold on McCormick's reaper, and the combine had trouble harvesting wet grain. So in 1853, Moore shipped his invention to the huge dry wheat fields of California. It was there that the combine began its ascent. By the end of the 19th century, the advent of steam power, followed by the internal combustion engine, replaced horses with tractors that towed the combines. But one more advancement remained.
After the Second World War, self-propelled combines became a reality. And with the evolvement of self-propelled machines, then the ability for a producer to gather more crop in an expedient manner really ballooned and caused a revolution in the ag industry.
Leading the revolution was John Deere's self-propelled Model 55 combine, an icon of grain production. What was once 5 men and 40 horses was now 1 man and 1 machine.
During that time frame, producers were getting larger. More acres were under cultivation. The demand for higher capacity machines was pushing the development of greater technology. And as that happened, then we developed larger machines.
The Model 55 brought in the harvest through the mid-1960s, providing the blueprint for the modern combine. It took the basic cutting and threshing mechanism pioneered by the first combines, gave it multiple speed settings, and made farmers more self-sufficient. In today's John Deere STS combine, the cutting and threshing operation has reached a new level in speed and efficiency. As the wheat enters the combine's header section, it is cut and then conveyed into the heart of the combine. Here, the threshing and separation process divides the wheat kernels from the rest of the crop. The actual threshing is accomplished with a rotating 26-inch diameter cylinder, lined with rows of threshing elements. When the cylinder turns, the threshing elements move the crop against a curved perforated plate, called a concave. This impact knocks the grain from the stalk, and the kernels of grain fall through the concave openings. The clean grain is then moved to the combine's grain tank. The wheat is then offloaded into trucks in a non-stop operation. What was once a grueling, tedious hand harvest is now a push-button, air-conditioned drive in the country.
I would equate the environment that the operator works in today much the same as people who work in an office. In an office, you expect a quiet environment, a comfortable environment, so that you can get your job done. Our cabs, our enclosures today are much the same.
These personal offices may be cushy, but they're all about the business of harvesting. Mechanization of the grain harvest was a natural progression of improved tools replacing human hand labor. But could technology develop a machine that simulated a human hand in the cotton fields? In 2001, wheat ranked third in value among all U.S. crops at over $5.7 billion. Approximately one-half of the crop was exported. It resembles a giant bug, eating its way through a sea of white. But this modern cotton picker is no slouch. It can harvest enough cotton in 10 hours to produce 20,000 shirts. It was called King Cotton, and the 19th century American South was dependent on it. The Cotton Revolution began when a Virginian named Eli Whitney invented the cotton gin in 1793. The gin mechanically removed the cotton seeds and allowed mass production in the South. But feeding the gin required armies of hand-picking slaves. When the Civil War ended slavery, the laborious task of hand-picking cotton continued. Dirt-poor sharecroppers and laborers endured back pain and blistered fingers to tear the small pods of fiber and seed from the plants. On average, an adult field hand could pick 90 pounds in a day's work. But harvesting productivity changed little through the middle of the 20th century. Cotton harvesting was finally mechanized in 1942, when International Harvester debuted the first mechanical cotton picker. By 1950, machines like John Deere's number 8 picker revolutionized the cotton harvest.
When we introduced the number 8 cotton picker, it was the first self-propelled 2-row cotton picker. In a day, it could do the same work as 80 field hands.
The pickers replaced human hands with rows of wickedly sharp spindles that grasp and spin the fiber from the plants. This modern 8-ton cotton picker harvests 6 rows of plants simultaneously and is capable of picking 70 to 75 acres in a single day. In a race with the weather, workers on the Stoneland Farm in Central California are using 2 6-row pickers to harvest 3,600 acres of cotton in under 30 days.
The main thing is to get it in before the rain, so we're trying to push as long as we can. We start up about 8 o'clock in the morning and work till 10:30 at night, actually harvesting.
Achieving such massive yield starts at the business end of the cotton picker. Each of the 6 picking heads contain 80 rows of spindles mounted on drums. The spindles rotate and spin the cotton bolls off the plant as they enter the picker's head section. The raw cotton is transported by suction and blown into the picker's holding basket. Getting the cotton out of the field and into the cotton gin is a logistics challenge. Vehicles called bowl buggies shuttle the cotton load from the picker to the module builder. They basically a massive compactor that compresses the fiber into gargantuan 12,000-pound blocks. The cotton's journey ends at the gin, where seed is removed from the lint. Meanwhile, the sprint to complete the harvest continues. While the hand-picking of cotton is now a distant memory, some field crop harvesting hasn't changed for thousands of years. In various third world countries, the hand harvesting of rice is still central to survival. The arduous task requires anywhere between 80 and 180 labor hours to reap 2.5 acres of rice. In various poor Asian and South Pacific nations, rice remains a crop that defies the economic benefits of mechanization. Much like wheat, the large-scale harvesting of rice in industrialized nations began in the years following World War II, as self-propelled combines mechanized the harvest.
It replaced the hand operations of cutting the grain, stacking it in the field, letting it dry, and then hauling the bundles of grain to a thrasher where they'd separate the straw from the grain. So the combine combined all those operations at once, and that reduced labor use quite considerably in rice harvest.
Mechanically, the modern rice combine uses the same principles as the wheat combine. The difference is in the ground. Rice grows in fields submerged in water. The water is later drained so the combines can begin the harvest. Because the ground is saturated, the first rice combines used tracks to cope with the muddy terrain. Today's combine can overcome the mud with wide, high-traction tires. In a 10-hour day, this machine can produce up to 6 tons of clean rice. Modern combines have pushed high-capacity harvesting beyond what was ever dreamed possible. The new challenge is equipping the massive machines with tools that gather intelligence. Computer-controlled monitors and sensors are driving a new farming philosophy called precision agriculture.
Well, the concept of precision agriculture is one that is trying to allow a farmer to farm on a large scale the way you garden in your backyard on a more intimate scale.
Today's combine has the ability to measure the quantity and the moisture content of the crop on the fly. Information the farmer can use to make adjustments and ensure the crop he is harvesting is at peak condition. The machine can also use global positioning devices to map the entire field and track the combine's location in it. By producing a yield map, the farmer can determine which areas of the field are producing less and for what reason. Using this precision intelligence, he can plot ways to improve weak spots for a more successful harvest in coming years. The harvesting of field crops may have become a satellite-assisted operation, but while impressive, such high-tech progression is irrelevant to hundreds of other crops, including the sugar beet. Sugar beets are root crops that grow and must be extracted from beneath the ground. The sugar beet is a much desired crop in a sugar-obsessed world. Extracting pure sucrose from a sugar beet is a massive enterprise of traffic control and basic chemistry. Centralized sugar processing plants coordinate a beet harvest season that can last more than 6 months.
Basically, sugar beets are harvested in what's called the campaign. The factory needs about 4,000 tons a day to operate, and those 4,000 tons are assembled from various growers' fields, usually in a particular area at a given time of year.
Sugar beet harvesting was a one-at-a-time job that required a deft touch and a strong back. Sugar beets grow just beneath the surface, and workers used pitchforks to flip or pop the beets from the ground. Modern sugar beet harvesting begins after the leafy tops of the beet plants are cut or flailed.
Once they're flailed, then the harvester is brought into the field, 4 rows typically, and they have lifter wheels.
2 29-inch in diameter pre-hardened steel lifter wheels rotate at a 65-degree angle and pressure or pinch the sugar beets out of the ground.
They come right down below the beet and lift it right up and drop it onto a conveyor belt which rolls around the big drum, which helps knock off any loose soil because you don't want to ship soil to the factory.
A Ferris wheel conveyor then delivers the beets to a parade of trucks waiting to speed the crop to the processing plant.
100 pounds of beets will give you 15 pounds of sugar. Every 100 pounds, by the time you get to 48,000 pounds, which is about a load of beets, you got over 7,000 pounds of sugar in that truckload.
In addition to processed sugar, sugar beet juice produces molasses, while the pulp provides a high-quality feed for dairy animals.
So it's a very complete utilization. I like to call the sugar beet the hog of the plant world. Every part is used.
Mechanization has transformed the world of field and root crop harvesting. But when a crop is soft and delicate, machines need a little help. In 1965, a tomato with a thick skin came to the rescue of a failing industry. More than one-half the sugar produced in the U.S. comes from sugar beets. The rest comes from sugar cane. At thousands of farmers' markets and supermarkets, consumers expect to find fresh, hand-picked fruits and vegetables. And in most every case, that's exactly what they get. Fresh market produce is a hand-harvested commodity. Mechanized harvesting is typically reserved for those fruits and vegetables destined for processed products, such as juices, sauces, soups, and a host of preserved canned goods. The economic impact of mechanized harvesting is nowhere more obvious than the processed tomato. Rising costs and a labor shortage in the 1960s prompted scientists at the University of California at Davis to seek a mechanical solution. But tomatoes had special needs, so researchers turned to age-old plant breeding techniques.
The problem was to develop a harvester that didn't destroy the tomatoes. Tomatoes aren't like wheat. Tomatoes are soft and fuzzy creatures, and you can't go out there and mash them in the field. It required a tomato that had relatively tough skin and was resistant to being handled by the harvester.
With tomatoes, they had to develop a variety that matured all at the same time rather than stretched out over time, because they developed a system of mass harvesting where they harvest everything at once. So they had to have all the tomatoes red at the same time.
The thick-skinned fruit saved an industry. Today, the machine-friendly tomato is planted extensively, and production costs have decreased by over 30%. The dusty task of picking and sorting used to require an army of laborers. The modern tomato harvester and 4 workers can pluck nearly 50 tons per hour. The machine lifts and consumes the entire vine as it moves through the field. As the tomato vine enters the harvester, it passes through a 4-inch gap that strips off the dirt. A large brush then separates tomato from vine. The vines are mulched and spit back into the field. Next, color sensors use photoelectric cells to distinguish between ripe red and unripe green tomatoes. The green tomatoes are ejected back into the field as fertilizer. Human sorters perform a final quality check before the tomatoes exit the harvester into a constant stream of waiting truck trailers. In a 90-day harvest period, a typical harvester operates around the clock, ultimately picking approximately 70,000 tons of soon-to-be processed tomatoes.
Innovations like mechanical harvest have allowed that industry to stay in business, and that certainly is one of the key motivators for growers to look at mechanical harvest.
For some crops, the transition to a mechanical harvest was a simple one. Nowhere is this more the case than with a nut harvest. Nuts have hard shells, and careful handling isn't an issue. In North America, Old World walnut trees were first planted in the West when Spanish Franciscan priests established the California missions in the late 1700s. These first trees sprouted an industry that thrives today. Walnut harvesting was traditionally a hand operation. Workers using hooked poles shook individual branches, while oftentimes women and children stuffed the sacks. In the 1940s, a unique style of harvesting replaced the hooked pole with a variety of machine-driven limb shakers. Today, the mechanized walnut shaker moves quickly throughout the orchard on a single mission.
It's designed to grasp the trunk of the tree and shake the whole tree at one time. Today's trees are also designed to accommodate the new shakers, unlike the older, larger trees that we have to shake individual limbs.
The shaking is actually performed by counter-rotating weights in the shaker's clamp arm. When the vibrating begins, the spinning weights create a shaking pattern that transfers energy into the trunk. The shaker is closely followed by a swarm of support vehicles, intent on finishing the job.
Once they're on the ground, we have mechanical sweepers that come in and sweep the product into a windrow, or a narrower row of walnuts. Once they're into a narrower windrow, then we have a harvesting machine that comes in and physically picks them up off the ground and puts them into a cart behind the harvester.
A shuttle system ferries loads of walnuts between the harvesters and truck trailers, where the nuts begin their journey to the dehydrating plant. On average, an acre of healthy trees will produce 2.5 tons of walnuts. Mechanically harvested nuts benefit from a hard outer hull. A fall does little to damage the final product. In the case of the black ripe olive, handpicking is still the prevailing method because it decreases the chance of bruising the delicate fruit. But with harvest costs as high as 60% of total production, some growers are turning to sophisticated shaker harvesters. The canopy shaker features fiberglass picking rods that shake the tree branches, causing the olives to detach and fall. An operator guides the picking rods into position. The rods oscillate at 250 revolutions per minute as the harvester creeps forward at 3 miles per hour. The olives fall onto padded belts and are then conveyed through an air blast separator, which blows out the leaves and twigs. The olives are deposited into removable bins. On average, an acre of trees will produce 4 tons of olives. But the harvest is far from perfect.
Presently, we're able to capture approximately 80% of the fruit on the tree. In comparison, a hand crew probably gets 90 to 95% of the fruit. So we lose a little production by leaving it on the tree, but we're able to do it at such an economic advantage that there's more dollars at the end of the year for us.
Like olives, the hand harvesting of many fruit and vegetable crops is difficult and becoming more costly to growers. But in some cases, using technology to assist rather than replace workers makes for a highly productive harvest. In 1919, botulism killed 35 people who ate improperly canned California black olives. It took 10 years and safer canning methods to reverse plummeting sales. Central California's San Joaquin Valley is the richest farm belt in the world. Its mild climate and nearly 6 million acres of farmland play host to some 350 different crops. Harvesting these crops requires a delicate balance of mechanization and hand labor. Where machines can't feasibly do the work, farm laborers, usually hired on a temporary basis, provide the muscle. For decades, California has depended on its neighbor to the south to supply the workers. The stream of Mexican labor began during World War II, when Franklin Delano Roosevelt initiated the Bracero program. Known as the strong-armed ones, the Braceros were a temporary labor solution to replace farm workers drafted for war. The solution proved not so temporary, and eventually nearly 5 million laborers came to the U.S. under the program, which ended in 1964. But the stream of Mexican labor continues today, often illegally. This ready supply of low-wage farm labor often reduces the grower's incentive to mechanize the harvest. And for the workers, the physical price of bending and lifting heavy loads is often very high. For them, a field of study known as ergonomics is making life better. Ergonomics focuses on the capabilities and limitations of the body in relation to a specific job, then tries to reduce heavy loads and prevent injuries from poor posture and repetitive motions.
We say, well, are there ways that we can give them better tools? Are there ways that we can allow them to do less bending and twisting? Are there ways that we can have them not lift loads at all or not lift so much of the loads?
The hand harvesting of lettuce was a difficult job that ergonomic studies began targeting in the 1970s. The mass harvest of lettuce still requires a bend and cut motion, with the worker trimming the outer leaves. But in the days prior to ergonomic study, workers packed the heads in heavy boxes and hand lifted them onto trucks. Back injury was a constant problem. At Dole Fresh Vegetables in California's Salinas Valley, a harmonious union of man and machine increases productivity and removes the worst physical stress. Like a giant factory on wheels, the lettuce harvester creeps slowly through the field as two-person teams pick and package individual heads, wrapping them in bags and placing them in boxes. Once a box is filled, a power assist roller helps the worker place it on a staging line.
The loader used to have to pick up the 40 to 50-pound box from foot level and put it up on top of the deck. Now that's being done automatically by a conveyor. We used to have somebody get out there and staple boxes shut. We now have that automatic taper, which as we've conveyed the box up on top of the deck, automatically shuts it and tapes the box shut.
For restaurants or institutional customers that require unwrapped or naked lettuce, a second harvester uses a precision pack method. Here, the lettuce is actually machine packed prior to its journey for post-harvest cooling. The labor-assisting devices in the lettuce harvest help Dole workers achieve an output of 5 million pounds of iceberg lettuce in a single week. But in some harvesting operations, ergonomic solutions are often surprisingly simple. The hand harvesting of wine grapes has changed very little over thousands of years. Workers cut the stems with hooked knives and place the bunches into bins. In field surveys, ergonomics researchers found that almost 60% of grape pickers suffered from persistent back pain.
So we said, well, what is it that we can potentially do about this lifting job? And one step is we could eliminate the lifting. Another step is, well, suppose we don't eliminate the lifting, but we just reduce the amount of weight they're lifting.
A full bin of grapes weighs 57 pounds on average. By designing a smaller tub to decrease the weight by just 11 pounds, injuries were reduced by 80%, with no noticeable change in productivity. The development of a mechanized grape mover, which mechanically lifts and empties the bins, is removing even more of the weight burden and speeding up the harvest. Because grapes are such a delicate fruit, hand harvesting is the desired method. However, a 400% increase in wine production in the last 30 years forced growers to consider a mechanized solution. The challenge, of course, in mechanically picking grapes is in doing so without bruising or damaging the fruit. The Core Van Orborotor harvester applies gentle vibration as it passes over the vine row. Nylon rods with rubber cushions penetrate the dense canopy. The rods oscillate at 700 to 1,000 strokes per minute in a circular motion. the gentle vibration causes the ripe bunches to release and fall straight down without damaging the grapes.
The idea of this is to simulate hand harvest to be as close as hand harvest for the premium and wine grapes and do the least amount of damage to the vines.
When the grapes detach from the vines, a conveyor captures the bunches and transports them on a series of conveyors. A fan system blasts the grapes with air to remove the leaves and other debris.
By doing this, the only thing that we're picking is the berries. No leaves and no damage, and we're putting them straight into the bin. It makes this easier for the winemakers because they have less foreign material to pull out, and it's just straight product that can go right into the press.
Depending on the grade of wine and the speed setting, the harvester is capable of picking anywhere between 3 to 30 tons per acre in a single hour. Such high capacity is a big advantage, but the rougher handling compared to the hand harvest can cause greater damage to the fruit. When the juices leak from damaged grapes, there is a greater chance for contamination, ultimately affecting the winemaking process. What the mechanical harvester has done for grapes is even more pronounced in the labor-intensive raisin harvest. The tried-and-true method used to involve hand-picking the fruit and wrapping them in paper rolls for protection. The raisins were sun-dried in the field and periodically turned over several weeks before retrieval could begin. A new mechanized technique called continuous tray harvesting duplicates the technology of the wine grape harvester while eliminating the long and expensive process of hand-picking and then turning the raisins.
The raisins are laid out on a thin sheet of paper, which is a 1/4 mile long usually, and a berry and a half thick. And what this allows us to do is get a consistent drying with no dirt and no human touching our raisins, and we're going for pure quality.
Cost-effective harvesting has built a strong case for mechanization. But the struggle between low-wage labor and the changing face of agriculture is a battle that is far from over. As science pushes the envelope in the fields of robotics and sensors, one wonders if the human hand may become obsolete in the coming high-tech harvest. Because raisins were so popular with Allied troops in World War II, their market price jumped from $48 per ton in 1939 to $312 in 1946. In the boundless orange groves of Florida, hand laborers work long months to harvest the crop. The vast majority of the fruit is destined to become orange juice. Unlike many crops bound for the processing plants, these oranges are still mostly hand-picked, and that's a cause for concern among growers. In Brazil, cheap labor is threatening to price Florida right out of the business.
Brazilians can produce orange juice and deliver it to the United States with a 20% tariff imposed on them by the United States and be cost competitive with Florida orange juice. And so the growers are looking at the real possibility that if they can't reduce their costs, they're going to be outcompeted in the market.
They've basically decided in Florida that they cannot compete on a worldwide basis unless they have a mechanized harvest.
Mechanizing the harvest would theoretically reduce the growers' harvesting costs. Until recently, an ample supply of low-wage labor kept Florida competitive. But the price of labor has increased, and a crackdown on illegal immigration is causing a labor shortage. The Florida Department of Citrus is conducting research into the daunting task of mechanizing the orange harvest. Various canopy shakers, shake and catch, and trunk shaking machine prototypes were evaluated in field tests. The best are able to reduce the cost per field box by 20 to 50% over hand picking. But many obstacles remain. In some cases, orchards must be redesigned with a uniform distance between trees to accommodate the large machines. And because so many orchards are small and independently owned, coordinating the mass effort will require time and patience. Florida oranges are but one example of the changing face of harvesting. Today, science is testing a host of new technologies to gather crops and ensure higher quality. Sensing technology is promising more precise quality control of the harvest. One scenario envisions offering consumers a better quality product with high-tech sugar sensors.
So that we want to develop a premium label, a batch of fruit that is guaranteed to be very high quality, and so the harvester would collect that and put it in a separate container. So you'd have a standard quality and a very high quality crop.
Creating a caste system for fruit, of course, might be a mixed blessing for consumers, driving prices way up on the high end. But other sensor technology currently in development promises to bring prices down. A device known as the electronic nose contains 32 electric-chemical sensors that simulate the human nose. By detecting the gas emissions of an orange, the nose is able to detect freeze damage, a devastating event that ruins the value of a crop. Being able to separate freeze-damaged oranges from healthy ones could save the industry millions of dollars in crisis years. Cost containment has always been the driving force of mechanization. Today, it is even threatening to take the farmer out of the combine. Named after the Greek goddess of the harvest, Demeter is a computer-controlled harvester equipped with a pair of video cameras and a global positioning sensor. This autonomous harvester is capable of harvesting crops more efficiently without the fatigue issues of a human-operated machine. Its precise guidance system turns the machine to cut successive rows in a non-stop operation while maintaining a straight-line accuracy of plus or minus 3 centimeters. The video cameras ensure that unexpected obstacles are avoided.